This is the Senior Design 2 project overview for Team 7. Our project is an FPGA-based digital signal processor. The application running on the FPGA-based DSP is a vocal harmonizer. The motivation for this project was to re-implement an existing non-real-time software vocal harmonizer. The pure software implementation of this system has significant latency as it is performing an FFT purely in software. Our goal was to re-implement that system with the FFT being done in hardware on an FPGA in order to enable real-time performance for this system. And we also wanted to gain experience with modern FPGA and embedded pipelines, specifically in the context of DSP applications. And the strengths and weaknesses of the final result. For the strengths, we did achieve real-time FFT capability. Latency was on the order of microseconds, so there was no perceptible latency between your input signal and your DSP operations and then your output signal. And we were able to achieve relatively accurate frequency shifting, moving the output of the FFT into appropriate new frequency bins, and then performing an IFFT, producing a pitch shift of your input vocal signal. For weaknesses, our frequency resolution was limited to around 47 Hertz due to our sampling rate and our point transform size, sampling rate being 96K and the point transform size being 2048. Our system is also a little unstable. It's very susceptible to input noise, and therefore our fundamental frequency detection for our input signal, which is the basis for all of the shifting algorithms, is a little unstable. So for our system design, the best place to start is in the FPGA, otherwise known as the PL fabric, the programmable logic fabric. Here we made a block diagram consisting of predominantly IP cores, which are just pre-programmed or pre-compiled Verilog or HDL that exposes ports for functionality that you interact with. This system programs the PL fabric in order to facilitate hardware fast Fourier transforms and inverse fast Fourier transforms. As you can see, our FFT core is located here, and then we have a subset converter for programming between an inverse FFT and a forward FFT at runtime. So nothing about this, core is really changing. It's pre-programmed to be runtime configurable. Then, as you can see, we have two PL control blocks for our audio codecs. We have two audio codecs. One records info. The other one plays the information back after it's been transformed by our embedded application, which we will show in a second. We also have offloaded work from the CPU on the board by implementing direct memory access blocks for the audio codecs. So as you can see here, the audio codecs write info to these cores, and then these program portions of the PL to actually write to the RAM on the board itself. And that is an overview of the hardware design portion of the project. For the embedded application, we have written a C program to control that custom PL fabric. There's a function for, based on hardware interrupts, sending information to the FFT IP core, reconfiguring it to perform an inverse FFT, and then moderating all sorts of other things, such as the audio codec recording being done and playback being done, as well as UART communication, because we have a MIDI controller connected to the system on a chip, which tells us where we should shift our vocal input signal to.
So this is our physical system. Right here you have the microphone input, which is fed into the audio codec on the board. From there, it's passed through the FFT IP core, and after that, we calculate the fundamental frequency and use that to shift the note or audio being played into the microphone to whatever the frequency bin is of the note being pressed on the MIDI controller. Once that's done, it loops through for the amount of notes that are being held, and then it passes that transform data through the IFFT, which then goes to the custom PMOD chip, secondary audio codec, and out to the mixer and speaker and headphones. So with the current implementation, it picks up a lot on the external noise in the room. So we have a few extra buttons down here to use preset fundamental target frequencies. You have 220 hertz, 440, 1000, 1500, 2400, and then this key right here, when you press it, it'll just lock in the fundamental frequency of whatever is currently being played into the microphone. So we'll start out by using a 1 kilohertz sine wave, and you're going to hear some of that noise from the audio codec itself. So now if we're to change that to another frequency, say we'll shift it up for this one, you can hear how the notes actually change. We shift it down, it's going to go a lot higher. And yeah, that is the basic overall system operation. So we're not limited, obviously, to just sine waves, and like I said, there is some external noise, but that is something that in the future will be worked out. But yeah, you can also use a vocal input. So, hello, this is Senior Design Demo, and now I can shift that. So, hello. You can also go lower. Hello. Senior design. By moving that around, we can also get it to go up or down more. Hello. So, with this being a project that we want to take beyond the scope of this class, we do have some steps that we're planning on taking after this semester is over. First of all, we're going to work on really targeting that audio quality issue and optimizing it so that you get a nice pure signal going through to the other side. We're also going to add windowing in so that you can get a more accurate frequency detection resolution. And then there are also external features that will be added in. So for example, right here, we have a Launchpad MIDI controller, which we can use to display different things, like show lights based off of different frequencies that are being played. You can also use it to press a note and have it preset to be 3 or 4 or however many notes you want automatically pressed. So somebody that doesn't have any knowledge of how to play the piano can still use a device like this with preset chords to do the pitch shifting with. On top of that, there's a lot of other audio stuff that we can do, but there's definitely a lot that we can do with this, and it's exciting to see where we'll end up. Thank you.